And we also have our guest speaker today, Fran Tanzella, a chemist who has been in the front field at the CMNS field since the beginning. He is currently continuing research at the Principle Science with the Energy Research Center in California in the US.
And Fran Tanzella first confirmed the Fleischmann-Pons anomalous heat effect at SRI International's lab in Menlo Park, California, back in 1989. And there, along with Michael McKubre, discovered new LENR science from palladium-deuterium cells by correlating the excess heat generated to the amount of helium produced, among other things. More recently, Fran Tanzella has been evaluating and testing the Brillouin Hot-Tube energy generator, now in development by Brillouin Energy Corporation. We have to add that Fran Tanzella has been described by a coworker as, quote, a superb technician able to get almost anything to work better than ever expected. Welcome, Fran Tanzella.
Glad to be here. Good morning, Ruby. Good afternoon, David and Alan.
Thank you.
Thank you. Well, let's get right to it. The Brillouin Hot-Tube is one of the few viable contenders in the world to be a marketable commercial reactor. And we've learned recently that Brillouin Energy Corporation is operating 5 different experimental cells right now. That's 5 experiments at once as they try to develop the Hot-Tube energy generator prototype. What can you tell us about these cells, Fran? What parameters are currently being explored in these 5 experimental hot tubes?
Well, Alan, they're both exploring the electronics, the pulses, what's necessary for stimulation, as well as the materials, which, as you know, is always the greatest problem in this field. And so they're looking at better dielectrics, better metals, better coatings of both of those materials, as well as better electronics to get the pulses more likely to stimulate the effect with more power and less failure, to be totally honest.
Thanks. Yep. You did mention that you might you're working with 1 or 2 other stealth groups. I don't expect you to tell us anything too much about them, but I'm glad to hear it. Do you think that activity is picking up recently?
I think so. I think the people that I've dealt with, and like I say, 3 of the groups are stealth in that they're not really coming out at the meetings recently or admitting to what they're doing, although 2 of them have actually been at the most recent meeting in Assisi, and a 3rd one was just over here. I was doing some experiments for them recently, and when they first showed up, I had 3 of these comic books sitting on the conference room table behind me, and the first thing they said was, "Put those away. We don't have anything to do with cold fusion." So and then there are other groups working with a startup doing solar photovoltaic and solar hot water simultaneously, totally unrelated to the field.
Back in 2016, it was at ICCF 20 in Sendai. You described the core of these Brillouin Hot-Tube reactors that Robert Goddess of Brillouin Energy is designing. And it's a cylindrical reactor with a sprayed nickel outer casing and interior layers of various metals and ceramics. And I understand the Q-pulse, the electromagnetic stimulation that controls and scales the reaction, is applied on the surface and then kind of returns through the center. Can you talk about those different layers and what are they currently what are they made of today, and how does that Q-pulse operate with those different layers to initiate and scale that reaction?
Sure, Ruby. First off, the metals in the middle, first layer down is copper, and that's simply just a return line. It's considered not active in the process. The middle layer is a dielectric with a high dielectric constant. Right now, Brillouin is considering that to be proprietary, and it can be different materials, although it's important that it have a high dielectric constant. The third layer right now is nickel, as they come in from the concept of the nickel hydrogen part of the field. As you know, the field is extremely diverse and has really diversified from the original Pons Fleischmann electrochemical effect. So they're using nickel, and they're putting it in up to 10 atmospheres of hydrogen in a sealed environment. That's pretty much the basic set of materials, but of course things get tweaked and changes, and we're always trying to make it better. As for the electronics, I'm not an electrical engineer, so I have to defer to Robert Goddess and his group. He has a nice group of electrical engineers, as well as physicists and chemical engineers and mechanical engineers. But the concept of the Q pulse is, if you have a narrow pulse, but that requires that the rise time of the pulse be very fast. And it's well known in electronics that a fast rise time yields the equivalent of a large set of frequencies. And ideally, you would want to access the resonant frequency of the metal, which is in the terahertz regime. And although there are some terahertz oscillators, they don't have the power necessary to do this. And so by putting in a narrow pulse, you achieve some high frequencies. And these high frequencies are well known in the field as leading to something called the skin effect. And the skin effect comes with magnetic materials with certain magnetic permeability. As the frequency goes up, the amount of current goes through a smaller and smaller amount of the metal. And it tends to be placed, or not tends to be, is required to occur at the interface with the highest dielectric constant. So most of the current, probably 95% of it, is going through a very narrow layer right next to the dielectric material on the nickel. And the concept is that's what's stimulating the effect.
What type of calorimetry are you using, and how are you measuring the heat?
Yeah, that's a great question. And that goes all the way back to 6 years ago when we first interacted with the Brillouin group. We helped design their calorimetry so that they can be more precise, more accurate, and higher efficiency. And so we pushed them towards mass flow calorimetry as well as heat flow calorimetry. And right now, almost everything is being done in mass flow calorimetry. And so the reactor is inside a cylinder that's extremely well insulated with water flowing through the outside of it. In mass flow calorimetry, you measure the input temperature of the water, the flow rate of the water, and the output temperature. Knowing those three parameters and the heat capacity of water, you can calculate the amount of heat coming out. On the other end of that, you have to measure the amount of power going in order to get your efficiency, in order to perform good calorimetry. And that's done two ways. There are oscilloscopes and termination resistors that are used to measure the power directly going into one of what they call their catalyst tubes. And also all of the electronic components have mass flow calorimetry around them to take away the lost heat. And so if you measure the power at the wall going into the power supply and then subtract all of the power that comes out from the heat generating electronics, what you're left with is essentially the same number you measure on the oscilloscope. And so you can measure either total power out over total power in, or you could just measure the power going into the reactor itself divided, coming out of the reactor itself divided by that going into the reactor.
Thank you.
That was great, Fran. I'm sure you've had some fun with that. Yeah, I find calorimetry the most difficult and frustrating aspect, practical aspect. I wanted to ask you a kind of a related question. Are you seeing any particle emissions inside the Brillouin system? Things like, for example, very low energy gammas that don't really escape the reactor?
We are trying to measure those. That's a great question, Alan. And yeah, and having spent 30 years doing calorimetry, I agree with you. It can be very frustrating. But yeah, that's a great question. And we have brought to bear over the last 6 months in one reactor, a sodium iodide gamma spectrometer. Now, also, in addition, we've added a neutron activation metal, actually trying our second one right now. But so far, we've not had any success measuring either gammas directly or gammas or X-rays coming from the neutron activation material.
Okay,
but we're continuing.
Never give up. Right, question 4, Ruby.
Well, you know, it seems now that more labs are getting excess output power in the tens of watts, which is up from the single digits that had been the norm for many years. How do we get to the next magnitude level of thousands of watts? And do you feel like we need to have that kind of thermal power output before any technology is can be developed from this, or do you see that these lower output powers have an avenue for some technology and development?
Well, there are different products I envision coming out of this field, and you're right. Some of them are going to require that you have thousands of watts, but I think some of them will probably work well in the hundreds of watts, say domestic hot water or hydronic heating, or even just forced air heating at a domestic level. For an industrial level, or even distributed power, you're correct. You need to be in the thousands of watts. And how do you get there? Being trained as a scientist, I like the scientific method. And so we need to really iterate on the theories and find better ways to test them. And back to Alan's last question, that's the main reason why you look for gammas or neutrons, is it helps you either confirm or help you iterate on your theory so that you learn something new and hopefully move forward and make a better design. But I don't see right now what's the real point of doing that much power until you can get the reproducibility up. I feel even some of the people I work with in this field are putting the engineering a little too early, trying to get to more power before they've really answered the reproducibility problem.
Well, you can hardly blame them.
Well, it's necessary, and it's absolutely optimistic, and it can be very economically viable for people who can get there.
Mm. Well, Fran Tanzella, I have one last question for you, and it concerns our comic book that we've just recently released, Discover Cold Fusion. And here it is. And I know that you've seen our comic book, and I had a little review session to get some reviews from the scientists who lived this story to determine how close we were to the truth. And I want to thank you and Michael McKubre, and also Ed Storms was there. And I want to apologize because during that session, we just blew right by you and didn't even acknowledge your presence. But of course, there you are in our comic book right there. And what if you could just now take a moment, what we should have done before, and talk about what you thought about this comic book in general, and if you think it's exaggerated, or is it pretty truthful, or what are your thoughts about this new advocacy tool using art?
Well, I think it's great. I think it's going to reach a whole new audience. I also feel it's going to reach a younger audience that we absolutely need. And yes, you're pointing to the caricature. When I told
Yes.
Robert Goddess yesterday I was doing this interview with you yesterday, he complained about his caricature, but I have no complaints. But
You know what? I think everybody complained. Everybody.
that's what I said to him. But anyway, those two middle pages are one of the most important parts in my mind, in that it shows how diverse the field became immediately. It was more than just geographically diverse, it was technically and scientifically diverse. And that's how the field has grown, that people have gone off in their own little area and found things. And I've had a great time working with many of these people. As I mentioned before, I spent 2 days with Professor Arata in 1998, and then spent months faxing things back and forth as it was done in the day. And I spent up to 7, 8, 10 weeks in Sapporo, visiting the lab there, the government sponsored lab there. And all of these people, you talked about spending time talking to Pam Boss. Before I left SRI, Pam and I used to talk once a month. And it's great to talk to all of these people and communicate. And the LENR forum and the CMNS news group are other great ways to communicate with them.
Thank you for that, Fran. Actually, you kind of drove by my next question there, because working at SRI, you were, a co-worker, or sometimes you just met some legendary figures in the business. Ken Shoulders, for example, was a co-worker, I know, and Les Case, Patterson, and so on, the Patterson Power Cell. You were there when all this was happening. And you mentioned Arata, obviously, with great interest in and affection, but I wonder who else has made an impression on you.
Well, I actually liked Les Case. He used to call regularly, and he was always surprised that I recognized his voice, although he had a very distinctive drawl. But because he was moving as an engineer, Les was trained as a chemical engineer, towards something very large. And it's actually been picked up by Dennis Cravens, and Dennis is probably the best person to have picked that up in Les's passing. But boy, I spent very little time with James Patterson, but one of his co-workers, Alf Thompson, I spent a fair amount of time with. And then actually after Patterson's death, his daughter got involved in things like that. And boy, and I spent time, well, Vittorio Violanti is probably the closest person I've worked with, if not that often in person, but he used to come over. And then the Naval Research Lab in Washington, D.C. I used to have to go to Washington on other business, and I'd always spend time visiting with Graham Hubler and the rest of the group there, David Knies, David Kidwell. There are just so many people, and yeah, and you have Mizuno. In fact, we had a nice call with Mizuno a few years ago trying to put a project together. Unfortunately, it fell apart. But it's always great to try and deal with these people. And then, of course, my most recent publication, we had back-to-back papers where one paper was with Pam Boss and Larry Forsley, and then the second paper was myself and the late Andre Lipson and Alexei Rosetsky. And so, yeah, there's just so many names over the 30 years.
I think, thank you for that. This field is full of fascinating people and some great minds as well. Yes, yeah. And I envy you I envy you a lot of that, actually.
Well, the ones that are still around, please take advantage of spending time with them.
Fran, I'm looking forward. I'm looking forward to hearing your stories. Or when I make the documentary movie next summer and swing by and do an interview with you, I want to hear all your good stories then.
Yes, well, I'll have to look them all up, because after 30 years, you got to dig pretty deep into your brain to find some of those.
Well, start thinking now.
I will.
Yes, a big thank you, big thank you, Fran Tanzella of the Energy Research Center, for speaking with us today. We hope to see you again in the future, and see you soon again.
Well, yes, I look forward to the summer, and it's great speaking to all of you. I'm going to put, a plug about the website. Of course, BrillouinEnergy.com will be Brillouin's website, and they just redid it. So there's a lot of new stuff on it. I've actually secured a domain, and I have a trivial website there called energyresearchcenter.net, and I am committed in the next 2 weeks to finishing it up and making it look professional.
Nice.
So, and it's been great talking to you, all of you.
Yes, thank you for discussion today. It was really interesting. You can find more episodes on LENR Call Talks on LENRforum.com. And Alan Smith, Ruby Carrett, and I hope to see you again for another talk about the state of the new energy science for green zero carbon future.
All right. Thank you.
Thanks.